Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 4.60. Problem statement says methanol is synthesized from carbon monoxide and hydrogen in a catalytic reactor. The fresh feed to the process contains 32% mole carbon monoxide, 64% hydrogen, and 4% nitrogen. This stream is mixed with a recycle stream in a ratio 5 mole recycle per 1 mole fresh feed to produce the feed to the reactor, which contains 13 mole percent nitrogen. A low single pass conversion is attained in the reactor. The reactor effluent goes to a condenser from which 2 streams emerge, a liquid product stream containing essentially all the methanol formed in the reactor, and a gas stream containing all the carbon monoxide, hydrogen, and nitrogen leaving the reactor. The gas stream is split into 2 fractions. One is removed from the process as a purge stream, and the other is the recycle stream that combines with the fresh feed to the reactor. I've got a picture of the process here written out with all the information that they give to us. Part A. For a basis of 100 mole fresh feed per hour, calculate the production rate of methanol, the molar flow rate, and the composition of the purge gas, and the overall and single pass conversions. Okay, so basically we just have to solve for all of these unknowns, and there's a lot of them. And we've got a reaction that they gave to us but didn't actually show, they didn't give us the actual reaction equation, so we'll have to write that out. Yeah, but we have all these different streams coming out, and this recycle stream I've labeled recycle so that you can see stream 4 kind of recycles back around and mixes with stream 1 and stream 2. Okay, so right off the bat, we want to look for equations that only have one unknown in them. So we'll find the process that has the most information given to us. It's kind of like solving a Sudoku puzzle, where you look for the line that has like all but one of the numbers missing, and then you fill in that number. Well, it's kind of like that in this problem, where you look at, okay, which element do we have the most information about? And that is nitrogen, right? Because they give us nitrogen right here, and then we know that it's recycled at a certain amount. Whereas none of the other products, we only know how much is going in for all the other ones. Okay, so right away I'm thinking, okay, I'm going to start off with my nitrogen balances and see what I can get. Okay, so I'll write out my reaction, and I'll say, okay, nitrogen is not even part of the reactor, so I know I have a lot more information about nitrogen going in, because nitrogen is inert and it doesn't participate. Okay, so let's draw a box around the entire process and say, okay, we're doing our nitrogen balance over the whole process. Okay, this is how much is going in, this is how much is going out, but there's nothing going out here because only methanol is leaving there. So basically we just have this equals this. But there's still 2 unknowns there, so we can't actually calculate it, but we're getting pretty close. Okay, so now we're going to do a nitrogen balance around the recycle mix point. The recycle mix point is this part right here. Okay, so we'll look at how much is going in. We got streams 1 and streams 4 going in, and then we have stream 2 going out. Okay, and then we start combining, because we have some process specifications. We know that the ratio of stream 4 to stream 1 is 5, and we know that stream 2 is stream 1 plus stream 4, which is 1 plus 5, which is 6. Okay, so combining these process specs that they gave to us, we can calculate, we can kind of get rid of some of the unknowns in here, combine like terms, and then we find out, hey, there's only one unknown here. Let's solve for it, nitrogen in the recycle. Perfect, we got that. Hey, now that we know this, let's go back up here. Hey, that was one of the variables we were missing because N4 is equal to N6. Right here, N4 is equal to N6. Why is N4 equal to N6? Well, the recycle, N4, the recycle, comes off of the exact same stream as N6 does, right? So they are the same stream. Their flow rates, so N sub 4 and N sub 6, their flow rates are going to be different, but they're going to have the same composition because they're not going through some sort of process, or they're not being condensed or reacted or anything. It's just a valve and you're splitting it, right? So some goes one way, some goes the other way. All right, so same concentrations. If N4 equals N6, then we have one of the unknowns there, so now we can calculate what N6 is. Boom, N6. Got another unknown there. Okay, so now I'm thinking, all right, now we have a lot more information since we know all the nitrogen stuff. It's going to help us know what the total flow rates of all these different streams are. Okay, so if we know what the total flow rates are, then we might have enough information to solve for carbon monoxide and hydrogen now. Okay, so let's do our carbon monoxide, hydrogen, and methane balances. So we've got our carbon monoxide, have two unknowns there, so we can't solve for that one yet, but maybe if we do our hydrogen here. Okay, so we do very similar balance with hydrogen, and still have an unknown here, and we have N5 in both of these. Okay, that should be red. N5 in both of those, so that still has two unknowns. It's not going to work, right? Can't solve it. However, look at this. We could remove N5 from the equation. Remove N5 by combining these two terms. So let's combine equation 1 and equation 2. 1 times 2 minus 2, right? Then that gives us this equation, which N5 is not a part of. And because H6 and CO6 are combined in this process way, where if you add up all of the mole fractions of a single stream, it equals 1, right? Okay, and we know what XN6 is, okay? So now we have our second equation. Two equations, two unknowns, and we can solve for those. And then the same thing holds true. Again, we know if we know 6, we know 4 because they're the same stream, they're going to have the same mole fractions, just different flow rates, right? Okay. Now that we know both of these unknowns, now we can go back to one of our previous equations and solve for what N5 is. There we go, that's N5. We're starting to fill in a lot of the blanks here, okay? So now we go back to our balance around the recycle mix point, okay? And we'll do our total balance. Finish writing these out because I don't think I wrote them out before. I had some of the process specs written down, but I didn't actually write down the values here. Okay, we got our process specs written down, N2 and N4. Then we do our balance with carbon monoxide. It's not carbon dioxide, excuse me. Carbon monoxide. And we solve for the only one unknown there. Perfect. And then we have H2, and we solve for the only one unknown there using our process spec that the mole fractions sum to 1, okay? Okay, so I was tempted to try and do a balance around the reactor because we have one stream going in, one stream going out, and we have a reaction equation, right? But we don't have enough information about the reactor to do a balance around the reactor. We don't have a reaction rate. we don't know the conversion rate. That's exactly what we're trying to solve for. What's the conversion, right? So we can't actually do a balance. If we draw a box around this, we don't have enough information about the reaction to be able to do that balance, right? Not enough information. So instead, we'll do a balance around the condenser. We haven't done that yet, okay? So let's go back to the condenser here. So do our balance around the condenser. I drew another little diagram here around the condenser. Now stream 7 gets split into 4 and 6, right? 7 equals 4 and 6. They have the same mole fractions, remember? Just different flow rates, but if you sum these two flow rates, they should equal stream 7. That's the stream coming out of the condenser before it gets split into the purge and the recycle, okay? This is what's getting fed in, and this is the information. We don't have any information that's what we're trying to solve for, right? And then we know this much methanol is coming out because we just solved for that earlier, okay? Okay, so now we write our nitrogen balance, our carbon monoxide, hydrogen, methane balance, and these balances are pretty simple, right? Because you just have in minus out, right? Okay, so then 4 equations, 4 unknowns, but these are very rudimentary equations, right? So then we can just add all those up and we find out what N3 is. And then once you know what N3 is and you know what each one of these components is, then you can solve for each of the components. So now we know all about stream 3, okay? We already solved for the purge gas, so I just wrote down the equation here. And then we wrote down the overall conversion of carbon monoxide. That's if you draw a box around the entire process, how much carbon monoxide is going in, how much is going out. Then that difference is how much is converted. So it's converted divided by how much you put in, okay? So how much was converted, how much did you put in? So 76% of the carbon monoxide that goes in to this process gets converted into methanol, okay? Then the reactor conversion rate, this is the reactor conversion rate, not the overall conversion rate. So for a single pass of CO2, or of CO, how much gets converted, okay? So how much do we have going in? We have stream 2 goes in. That's how much CO is going in. That includes how much is in the recycle. How much is going out divided by how much we're putting in again, okay? The reactor converts only 14% of the carbon monoxide that goes in. Only 14% is converted. That's why it's really important to have that recycle stream, okay? Part B, briefly explain in your own words the reasons for including the recycle stream and the purge stream in the process design. Okay, so we've got our recycle stream. You need it because you have a low conversion, right? Only 14%. If you didn't recycle that, a lot of your reactants would just go to waste, right? So it's much better to pass them through the reactor over and over again until they all get converted. Well, why don't you just recycle all of it? Why have a purge, right? Let's go back and look at our equation, or look at our process, right? Let's say we continue to just recycle everything back into the reactor. Everything goes back to the reactor. Well, what happens with this product? When does it leave? The carbon and the hydrogen will leave in this stream, but there's no nitrogen in this stream, right? So nitrogen needs a way to go out. If you're putting nitrogen in, nitrogen also has to go out, right? So if you only had this stream and you didn't have a purge stream, there would be no way for nitrogen to leave the process, okay? And then nitrogen concentration would just build up until either you had a pressure explosion or you just couldn't feed anything into the reactor anymore. Yeah, so, well, that is it for problem number 4.60. Thank you for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem-solving videos. Thanks again, and I'll see you in the next video.